Deep neural networks have achieved state-of-the-art performance on our most difficult computational tasks. They categorize millions of data points in milliseconds, providing the backbone for modern visual recognition and speech processing. This high level of expressiveness creates a specific expectation. Because these models solve problems with human-like accuracy, we tend to assume their internal logic is as robust as our own. But there is a gap between performance and robustness. These systems harbor a specific flaw that can be exploited by something the human eye cannot see. Take a standard image of a dog. A trained network identifies it with near total confidence. But researchers found that by applying a microscopic, mathematically calculated layer of digital noise to those pixels, the outcome changes. To a human, these two images are identical. But under the second photo, the AI now confidently categorizes the dog as an ostrich. This is an adversarial attack. It suggests that whatever is happening inside the network's layers is based on a logic that is alien to human perception. If this were a localized glitch, it could be dismissed as a simple error in a specific model's training. In 2013, researchers Szegedy and Ilya Sutskever published Intriguing Properties of Neural Networks. Their work uncovered a set of properties that challenged the existing understanding of how these models learn. The paper revealed that these adversarial perturbations are transferable. A set of invisible noise designed to break one network can often break others. This diagram shows the process. The exact same noise can be fed into different architectures, trained on different subsets of data, and still produce the same error. This transferability indicates the vulnerability is not a random artifact of one training session, but a property of the underlying mathematics. To find the cause, we have to look at how these networks store information. The search for the why leads to the AI's internal architecture and how it defines concepts. It was once assumed that individual units in a network's higher layers mapped to specific concepts. In this view, a specific node might light up only when the network detects a cat's ear. Szegedy's team found that this isn't the case. Mathematically, there is no distinction between one individual unit and a random combination of many units. Both identify the same features with the same level of precision. Concept information isn't tied to a single location. Instead, it is spread across a multi-dimensional space. The meaning of a cat is found in the coordinate system of the entire network, rather than in any one node. Because semantic information is decentralized across this mathematical space, the network's logic does not align with our intuitive preference for discrete, modular concepts. This sprawling coordinate system is the foundation for the visual vulnerability we saw earlier. The paper's second major finding is that because networks map inputs across these high-dimensional spaces, the resulting mapping is discontinuous. In this context, discontinuous means the network's logic contains microscopic drop-offs. These are hidden pockets of misclassification located mere fractions of a millimeter away from data the AI correctly understands. Researchers can exploit this by using an algorithm designed to maximize the network's prediction error. It calculates a path from a safe data point directly into one of these hidden pits. That calculation produces the imperceptible perturbation, the invisible static that changes the classification. The noise doesn't actually break the model, it simply acts as a guide, pointing the network toward the discontinuous blind spots it created during the learning process. These discoveries highlight a recurring tension between a network's expressiveness and its interpretability. The complexity that allows these models to succeed at difficult tasks is the same factor that makes their internal solutions difficult for humans to parse. While humans categorize the world through smooth, contiguous concepts, these networks build their reality on fractured mathematical maps. This distinction has practical implications, as these systems are deployed in critical areas like autonomous driving, locking onto pedestrians, and medical diagnostics. These models are performing millions of classifications, where a single error can have high stakes. Relying on these models means trusting systems that contain invisible, mathematically predictable points of failure. Ultimately, the study demonstrates that artificial capability is not synonymous with human understanding. In the world of neural networks, the most significant vulnerabilities are often the ones we are physically incapable of perceiving.